Once again, sorry for bad lighting, but this is page 10, 12, sorry, 12 series problems with the capacitor thrown in now. We're going to talk about it, hope do the lab, hope make that make sense, this will make it like much easier. So first question, we have this circuit and we're going to close the switch. So we're going to close switch 1. I'm going to close it. This is not a good marker. We're going to close switch 1 and see what happens. See what happens. What's going to be the charge on the capacitor? So, and when we close that switch, this one's still open, so you just get, this loop of current. You got to find the charge, voltage, and energy for this capacitor. Easiest one here is voltage. Hopefully, the first thing that you thought of was 12 volts, right? It's just going to be whatever the voltage of the battery is. So I'm going to say 12 volts. Now what's going to be the charge on the capacitor? So remember, the equation for capacitance is C equals Q over V. So C is going to be 2 picofarads. Pico means to the negative 12, and that's on your college board equation sheet. Flip it to the other side. It has all those constants and stuff, and it has a table of the P is for pico, and it's 10 to the negative 12. So 2 times 10 to the negative 12 farads equals Q over V. So Q is what we're solving for, and V is 12 volts. So what are you going to do? You're going to multiply both sides by 12. You should get, if I look correctly, you should get, and I'll box them. You should get 2.4 times 10 to the negative 11th coulombs. So make sure you enter that into your calculator right. Energy stored in the capacitor, we know that energy is equal to 1/2 Q times V. We have Q, we have V. You just plug it into this equation. I got so I got energy 1.44 times 10 to the negative 10th. Let me know if I made any mistakes with my calculator stuff, but hopefully you know how to use those equations. That's the important part. Second part is now we're going to open this switch up again, S1, and we're going to close S2. So we closed S2, and we got to find what is the initial current and what is the power by each resistor. So first of all, when you're doing any kind of these problems, it's helpful to know what the equivalent resistance is. And the equivalent resistance in this case is just 2 series resistors. So 4 plus 8, because 4 ohms, 8 ohms, you get 12 ohms. So R equivalent, I'll just write this down. R equivalent is equal to 12 ohms. And now, this capacitor is going to discharge. What's its initial voltage? It's 12 volts. So 12 volts. So 12 volts over 12 ohms, you get 1 ampere of current. Yikes, okay, that was way too much. What's the individual power by each resistor? Remember, power equals I times V. So power equals I times V. That's pretty lucky for us because 1 ampere, right? 1 times anything is just that anything. So it's 1 times 4 ohms, that's 4 watts. So power 1 equals, when I say 4 watts, right? Because I'm doing 1 amp times 4 ohms. 1 amp times 8 ohms is, what did I say? 8 watts. Cool. And I'll box them. So hopefully the first problem isn't too crazy, right? This isn't really anything to do with the lab, honestly. This is more just charging a capacitor, discharging it, that fun stuff. This is kind of using the key ideas from this specific lab though. So when we have this circuit, so it's these 10 ohm, 6 ohm, 4 ohm resistors, right? All in series with one another. But this 4 ohm resistor is in parallel with this 3 microfarad capacitor. Battery's 10 volts. So we just got to figure out when the thing is first connected versus a steady state, all these values, and then eventually the capacitance stuff. So remember, when it's first connected, and you can watch my video on this to make it make more sense, or whoever videos you want to watch. When it's first connected, this acts like a wire. So this like short circuits this resistor essentially, so no current's going to pass through it. I can redraw this, right? I can redraw this as like so. Only 2 resistors. So I could say first connected, it's going to look like this. So this isn't too bad to solve because, you know, this is 10 volts. This is 10 ohms. This is 6 ohms. The equivalent resistor is 16 ohms. And then from there, I can just do my Ohm's law stuff. So total voltage is 10 volts. What's the total resistance is 16 ohms. So 10 over 16 will get me the current by Ohm's law. That is like what, 5/8? I don't know. You should really plug it into the calculator. But 5/8 amps, whatever that is. And then now current's going to be the same for all of these. So I can just put 5/8 amps. This is a series. Whoa. Actually, never mind. So 5/8 amps for 10. 5/8. My mom's calling me because it's dinner. Yeah, I'm coming. For the 4 ohm resistor is not getting any current, so it's actually 0 amps, right? Remember, this short circuits, no current's going through here. Wow, that makes our job easy because 0 amps, 0 volts used, and 0 watts of power dissipated. Whole thing becomes 0, and then I can just multiply these values. So if I want to use Ohm's law to find like the voltage by the resistor, 5/8 times 6, I got actual numbers this time instead of fractions. 3.75 volts. And then for 10 ohms, it's 6.25 volts. And then power is I times V. So 5/8 times 6.25, I got 3.91 watts. And then for this one, 3.75 times 5/8, I got 2.34 watts. 10 volts times 5/8 would be 6.25 watts. Oh, this is 0.625. I think that's what 5/8 is, 0.625. Hopefully. Now let's do steady state. So after a long amount of time, this capacitor gets full of charge. No more current's going to go through it. You can kind of ignore it. Doesn't affect the circuit if we were to just take it out kind of thing. So now my steady state circuit, so if I were to write steady state, it would look like this. So 10 ohms, 6 ohms, 4 ohms. We're still in series, so the equivalent resistance is just the sum of those, which is 20 ohms. So our equivalent is 20 ohms. Okay, cool. So now we can just start solving. So total voltage, 10 volts, because that's a battery. 10 divided by 20, right? Because I'm doing V over R to get I. 10 over 20 is 1/2, so 0.5 amps. Still in series, so everything, right? Like everything, because, you know, we're including all 3 resistors. Everything has 0.5 amps going through it. The voltage is just I times R because of Ohm's law. So 0.5 times 10, 5 volts, and then 3 volts, and then 2 volts. I'm just halving the resistance really because 0.5 times 4 is 2, that kind of thing. And then now the power, I multiply I times V. So 5 times 0.5 is 2.5 watts, and then 1.5 watts, and then 1 watt. So I'm literally just taking the voltage and dividing it by 2 or multiplying by 0.5. And then for the power of the whole thing, 0.5 times 10, that's 5 watts. Cool. So now my capacitance, what's going to be the voltage going across it? Well, when this whole thing's filled up, the voltage and they're parallel, so whatever the voltage across this is equal to the voltage across that. That's our parallel rules. So this has 4 times 0.5, so 2 volts. So this will have 2 volts, this capacitor going across it. So 2 volts, parallel rules. Our charge, same thing we did here. To get the charge, we're really doing C times V. Capacitance times voltage. So that would get you, I think, 6 microfarads. Think so? Hopefully the units work out there. 6 microfarads. How much energy am I going to get? Now I do this equation, 1/2 QV. QV, I get 6 microjoules because 1/2 times 2 times 6, I get 6 again. So 6 microjoules. Hopefully this wasn't too bad. This is just an application of what we got from the lab. So hopefully this was kind of easy going. Parallel stuff, things that harder, that's fine. That's just life. That's just life. That's just how things are sometimes. Hopefully this made sense. Thank you for watching. Appreciate it. Appreciate it.